Hello, we are back to continue our lecture to the folder of lecture 3, okay, and the name of the folder is for this lecture set 3 is column generation for LP with too many variables and then 6-move decomposition, okay. We're going to start by, before reviewing the material contained in this folder, okay. First of all, in this clips, okay, we will try to revisit, okay, the classical, what we call the simplex method, and express that in matrix form, okay. And I think we should start with this one, okay. Before, I think this is a required knowledge, okay, before we get in touch with some of the main material. Okay. First of all, okay, we all know that to solve classical linear programming, okay, in general, we have a general method called the simplex method, created by George Bernard Danzig in 1947 historically. Okay, I will describe the simplex method, okay, and express that in a matrix form, which is normally the basic foundation before we implement computer software, okay. But as you know that nowadays there's so many modification and the hybrid approach of the simplex with other methods like the interior point method and some of the general optimization technique, okay, to find the best combination of uses to improve the efficiency of the algorithm for solving linear, especially large-scale linear programming. But still, okay, the simplex theoretically has been found that it's very weak in terms of computational performance in worst case, but in practice rather be very highly efficient and effective. Okay, so first of all, okay, let's look at linear programming in metric form first. Okay, we either want to minimize or maximize of the C function as a linear function as C transpose X, and C is a column vector of size n by 1 with X a column vector of n by 1. And for all the constraint to identify the decision variable X, okay, is expressed then as a linear equation of A times X equal to B, where A is a matrix of size n by n when m is less than n, okay, and B is a column vector of n by 1, okay. And this is for the default situation for the most of the linear programming. All variable contained in vector x are greater than or equal to 0. And you know that theoretically for linear programming, okay, the optimum solution is can be lies on what we call the extreme point, okay, of the convex polyhedron, okay. And in terms of linear algebra, okay, this extreme point, okay, can be expressed as by separate the vector of x. Now we write this as an x transpose, two type of variable. The first one we call the basic variable, the x sub b, capital B, and x sub capital N is a remaining non-basic variable, okay. And with the separation of x sub b and x sub n, okay, when A times x, okay, A can be separated into part also. The first part we call the basis, okay, or the basic, the submetric related to all basic variable, and n is a submetric related to all x non-basic variable when A times x here, okay. Certainly, when C transpose times X with separation of X, C can be separated into part also as a CB transpose and CN transpose. Okay, where once you separate the sub as a subvector or submetric, okay, the size with the condition m is less than n, okay, xb, okay, have the size equal to the number of basic constraint of a times x equal to b, which is m by 1. Therefore, the dimension size for x sub n is n minus m times 1. Okay, this leads to the metric size of B matrix as a square metric of m by n. And we will assume that the determinants of B is not equal to 0. Okay, and the remaining submetric n certainly have the size of m by n minus n. Okay, and the size of C sub B and C sub n also follow x sub B and x sub n. Okay, so this is the expression of the linear programming in matrix form. Okay, now in the next step, okay, we're gonna separate A times x here based on the separation of x sub B and x sub n. Okay, since A is equal to B submetric and augmented with the n, okay, and times x, x is certainly xb transpose, xn transpose, and all this transpose again. Okay, with this multiplication you get this relationship xb times x sub b transpose, and that lead to x sub b. xb x sub b plus n x sub n is equal to b. And certainly with if you multiply both sides by b inverse, okay, and b inverse can be exist in only situation that the determinants of b have to be non-zero. Okay, therefore x sub b is equal to b inverse b. Okay, once you multiply b inverse on both sides, this becomes b inverse, and b inverse times b they lead you to xb, and you get b inverse times n x sub n, and you move it to the right hand side to get this relationship. And then you can expand C transpose x by separating x sub b and x sub n in using a similar idea. When you apply for the A times x, okay, you get CB transpose x sub b, C sub n transpose x sub n, and then you substitute x sub b here in terms of x sub n using this relationship. Okay, put x sub b here, okay, with this relation here, substitute here, you get this, and then you rearrange the term, you get this one, the C transpose x will be equal to CB transpose B inverse times B plus, and this one CN transpose is according to this term, but you can have these two terms have x sub n in common, so you can put x sub n out and you put the blanket in. Okay, this one becomes CB transpose times B inverse times n. Okay, this one multiply to x sub n, and you get a minus sign, but so when you combine these two terms you get this. This is a well-known formula for what we call the reduced cost coefficients. What is the meaning of a reduced cost coefficients? It means that, okay, now you can see that you write C transpose x, which is the objective function, in terms of non-basic variable. Okay, it's well known that the property of non-basic variable is that it has to be equal to 0. Actually, to get the extreme point, okay, for any equation expressed as A times x equal to b, okay, is to separate the two variable x sub b and x sub n, and then you solve the remaining equation while you assign x sub n is equal to 0. Therefore, x sub b have to be equal to b inverse times b, because x sub n is always 0. Okay, but this one, once you write this in a general form, the reason why we call this a reduced cost coefficient is mean that at this moment x sub n, all x sub n is equal to 0. But if there is any coefficients, okay, multiply to sum of the x sub n which has the positive negative value, let's just say negative. Okay, if there exists some negative value in this vector that multiply to x sub n, okay, It means that if you increase the non-basic variable by 1 unit, you can reduce C transpose X by this reduced cost coefficients. Okay, because it's a negative value. Once you increase, the current situation is that non-basic variable is equal to 0. So that's why we call reduced cost coefficient. So you know that when you assign some positive value to that x sub-n, sum of that x sub-n that has a negative reduced cost coefficient, you can reduce, okay, the current C transpose X based on the B inverse B, the current x sub B. Okay, that's why we call it. And this is the idea that you can identify that, okay, I'm going to put this as an entering variable because you now have some x sub B which is a member of the x sub n, okay, that have a negative reduced cost coefficient. You want to identify this value as an entering variable. Choose one of them. If you have multiple of them, choose either one of them, or choose the one that have the most negative value. There are several rules, okay, for choosing the entering variable. Why you want to put you want to call this entering variable? Because the property of the optimal solution of the simplex method is that the x need to be expressed as a x sub b and x sub n. And x sub b there will be m members, okay, and x sub n have n minus m members, okay. So with this reduced cost coefficients, okay, you have you now know the trend that if you move some of this non-basic variable and you want to put it in x sub b, you can reduce C transpose X. And at the same time, it identify what is the optimality condition once you found, because if you found any x sub b that all reduced cost coefficients are all greater than or equal to 0, it means that you're reaching the minimum value of minimized xc. Because this expression show you that if you approach an x sub b such that all reduced cost coefficient associated with the non-basic variable are all positive, that solution have to be the optimal solution for this problem. Okay, so but if there's exists some x sub b, okay, which is a member in x sub n, they have a negative reduced cost coefficient, therefore you'll be able to identify the entering variable. Why you call this entering variable? Because you want to move this non-basic variable to x sub b, and also once you move one variable from x sub n to x sub b, you need to take one of the variable in x sub b out. You cannot have an additional variable too, because x sub b can only have up to m member, right? Because it's identified by b inverse times b. Okay, so if you want to put x sub b to x sub b, you need to find what we call the leaving variable. That leads you to this idea that, okay, and in metric form, okay, suppose you have a sub vector a sub b be the column vector of metric A associated with to x sub b, which is a member of x sub n, the non-basic variable. Okay, certainly a sub b is a member of n. And then you found b inverse, okay, at that moment, or what is the xb, you'll be able to identify what is b. And then you found b inverse times ae, okay, as one vector. And b inverse b is the other vector. We call a star e sub I and b star I sub b star sub I, okay. And then you find what we call the minimum ratio. The minimum ratio is that, okay, row by row, okay, for these two column vector of b inverse times a sub b and b inverse b, okay. You found the ratio when only the division, okay, part is greater than or equal to 0, which is the member according to associate to vector b inverse times a sub b. It means that once you found b inverse a sub b, okay, you found a column vector here. And then row by row, okay, in this column vector, you check whether the element have a positive value. For all positive value here, okay, you found the ratio, okay, use that as a uh, division, okay, and then divided that to the b sub I according to the same row b sub I in the column vector of b inverse b. Okay, so once you find this, okay, if there exists one I such that a star e sub I is greater than 0, you pick the minimum one. And as you might recall, that why we are doing this, we are doing this to just to guarantee that the new extreme point or the x sub b, okay, will always be positive. X means that x sub b inverse b is always greater than or equal to 0. That's why you pick, this is what we call the pivot point during the row generation of the simplex algorithm, okay. And then suppose that you have I sub L, okay, capital I, be the index of row according to that minimum ratio zeta, okay. With this identification of row I, okay, I sub L, you'll be able to identify what we call the leaving variable, which is the variable associated to that row, okay, in the x sub b, okay, the current basic physics basic variable. Okay, certainly when you know x sub L is a member of x sub b, okay, so you update new x sub b. New x sub b is you put entering variable in, and okay, you move the leaving variable out, and the leaving variable is added to x sub n, and then you move x sub b out of x sub n and put it in x sub b. Okay, with new update here, okay, you'll be able to identify what is the new submetric b and submetric n, and then you can repeat the process until all reduced cost coefficients are greater than or equal to 0. We have to go back to this one, reduced cost coefficient. If all this greater than or equal to 0, it means that you don't need any entering variable, because all the entering variable, once you move into the current basic x sub b, going to lead you to a higher value of C transpose x, because you know that x is always greater than or equal to 0. Once all reduced cost coefficients are greater than or 0, no, it's already been proven that C transpose x is at the minimum value. Okay, but if there still exists a negative value, so you repeat the process again by identify the entering variable, and then identify the leaving variable, and then once you replace the updating for the new x sub b and x sub n, so you can repeat the process again and again. And once all the reduced cost coefficients are greater than or equal to 0, the current solution found, the last solution found, is an optimum solution. Okay, and in more detail, you might recall, okay, that if suppose that you don't have any positive value from vector b inverse times a sub b, okay, to find the minimum ratio, it means that you're facing what the situation, what we call the unbounded condition. It means that the solution doesn't have, suppose that you want to minimize some objective function, the optimum solution is at reaching the minus infinity. Or if you want to maximize C transpose x, the new x keep finding and increase the value up to infinity. So you have unbounded situation. Okay, and that's about what I try to recall. Okay, the explanation of the simplex method in the matrix form. Okay, next we're gonna review, okay, a very important situation for the LP. We call the weak and duality, weak and strong duality. Okay, we already mentioned some of that in the previous clip, okay, but didn't express it in a written form of PowerPoint like this. Okay, given the primal problem in the metric form as you show on the screen, therefore the definition of the corresponding dual problem is like this. Okay, and you know that, okay, you can always, okay, whatever equation or inequalities, you can always transform them in terms of ax greater than or equal to b. Okay, and then with this as a primal, the dual according to the dual problem is the definition. okay. And then we can go to show you the property what we call the weak and strong duality, okay. For the primal problem, okay, you have a times x is greater than or equal to b here, a times a. Suppose that I transpose it and multiply by y, and you know that y is always greater than or equal to 0. So this relationship still holds once y is always greater than or equal to 0, because a times x is always greater than or equal to b. Okay, but this would not be right if you say that, okay, if ax is y is allowed to be negative value, right? So this is only true when y is always greater than or equal to 0. And we can do the same for the dual model of A transpose Y transpose times X, always less than or equal to C transpose X. This one we can go back and look at this formula, right? A transpose Y, okay, and then you transpose it again, and then you multiply them by X. This one is C transpose and X also, okay. But you know that X is always non-negative, X greater than or equal to 0. Therefore, this relationship still hold. Okay, once x is cannot allow to be a negative value. And then after that, okay, you look at the relationship here. You want to prove whether ax transpose or all of it transpose times y is the same as you are doing A transpose y transpose x. This one we want to show you that the left hand side of these two inequality is the same. Okay, look at the ax transpose y, okay, you know that a times b, okay, all a times b transpose is equal to b transpose times a transpose. So this one a times x altogether transpose, leading me to this result. The x transpose times a transpose, okay, times y, okay. But this value is a scalar value. One is a scalar value because it's compared with b transpose y and c transpose x. It's a no dimension of 1 by 1. So if I'm going to transpose it again, it's going to doesn't make any difference, because 1 transpose is always equal to 1. Okay. So when this one is transposed again, okay, we can apply the concept that A times B all together, okay, transpose is equal to B transpose A transpose. Okay. So this one we gonna do this, okay. We move here, okay. Once we have A, B, C transpose, okay. So you're gonna get C transpose, A transpose, C transpose, and B transpose and A transpose, okay. So this one is like this, okay. Let's look at here, okay. If you have X transpose and transpose again, you get X here. And A transpose Y all of it transpose, okay, because this is a transpose here. This is the second. A is like A is equal to X transpose and B is equal to A transpose Y, okay. So A times B transpose will be here, like now B is A transpose Y, A transpose Y transpose, and X transpose and transpose again, you get X value. So this one just want to show you these two terms is the same. Okay, by using a metric properties, okay, and with these two is the same values, therefore you can conclude that C transpose X is always greater than or equal to B transpose Y. Okay, based on this, and that's is a well-known property for all x, y in the feasible solution space for each of the problem. Okay, X is for the prime problem, Y is for the dual problem. So this is what we call the weak dualities, okay. And you know that based on the original problem that we formulate, the C transpose X is aimed to be to minimize, and B transpose Y is aimed to be maximized. Therefore, the only point that this inequality will be whole for all x, y is only in this case that the maximize of B transpose Y is equal to the minimize of C transpose X. That's the only point that this the weak duality can be changed from less than or equal to equal. Okay. If there exists maximize B transpose Y greater than minimize C transpose X, the weak duality will not be whole for all X, Y anyway. So the only point that you can change inequality less than or equal to equal is this point, and it's only unique point at the optimum solution in both problems. This gives you the idea that once you will be able to find the optimum condition, the optimum solution with the optimality condition based on the reduced cost coefficients, okay, you're gonna get B transpose Y, and you know that C transpose X and minimize for any is always equal to CB transpose B inverse B, because all the xn have to be 0, okay, in order to satisfy the extreme point condition for n-dimensional space expressed that for the constraint of A times X is equal to B. Okay, so when you compare the coefficients here, okay, this is a scalar value you can transpose on both sides. Okay, if I transpose from this side, this is gonna get Y transpose times B. Okay, and you have when Y transpose times B now is the same. So it's very easy to see that Y transpose is equal to CB transpose B inverse. Will be the optimum solution at the optimum of X is equal to B inverse B. This strong duality gives you the idea that when you're using the simplex algorithm, okay, you be able to identify B or N. You can get the optimum solution of both primal and dual solution at the same time. Once you reach solution for either, you can choose either one of the model, either primal model or dual model. Once that model solved, you can get the solution of the dual solution of the other problem simultaneously. Okay, so this is all the basic that I try to show you. Okay, review the part, probably a very quick view, and it's a requirement that you need to be able to understand the basic idea of the simplex method also. And as you know that in order to develop efficient algorithm to support the simplex method, or heavily rely in each iteration relies on the updating of B inverse from one iteration to the consecutive iteration, because you are dealing with the replacement of a column vector in A sub n to A sub b. Okay, and iteration by iteration you can directly solve for B inverse, but it's going to take some time. But you'll be able to, what we call, in technical term, we call the rank 1 updated. Okay, because from iteration to the consecutive iteration, there will be only one column difference. Okay, in B matrix. Okay, so in order to update the B inverse, you don't need to restart calculating the B inverse from the start again. Okay, that's you might recall that the basic idea of what we call the revised simplex method. Okay, but nowadays with the advancement of the computing facilities, okay, now we'll be able to solve this simplex algorithm very efficiently using the current hardware technologies. Okay, and that's about the reviews of the simplex method and weak and strong duality in metric form. Okay, we will use this type of notation and idea, okay, in the next script. Okay, and we will go back to the illustration by example under the Excel platform and MATLAB platform. Okay, this is a topic that we will discuss in the next script. We call linear programming with too many constraints, or either too many variables, or can be both. Okay, simultaneous, too many constraints and variables. Okay, so that's about it for this script. Okay, see you in the next script.